Good morning, everyone. So, today's topic is DC generator characteristics. In previous classes, we have discussed about what is generator and working principle of generator, and then we have discussed about the types of generators. Right. So, what are the types of generators? Types of generators are shunt generator, series generator, and compound generator. Right. So now we are going to discuss about the characteristics of DC generators. So we have mainly three characteristics. One is open circuit characteristics, second one is internal or total characteristics, third one is external characteristics. Okay. So before going to the characteristics of DC generators, what is the relation between generated EMF and the flux produced? And then you see, so what is the relation between generated EMF and flux produced, right? So actually we have discussed generated EMF is EZ equal to pi z NP by 60A, right? See, so whenever a rotating conductor is placed in a magnetic field, it produces the induced EMF, right? According to the Faraday's laws of electromagnetic induction, right? See, so here phi is the flux per pole, P is the number of poles, N is the number of revolutions made by armature per minute, and whereas Z is the number of armature conductors, and capital A is number of parallel paths. Okay, so this we have derived in the previous class, right? So EZ is equal to pi z NP by 60A. See, so what are the constants here? Number of poles, number of armature conductors, number of parallel paths are the constants. So EZ can be written as EZ equal to K phi N. Okay, so where K is the PZ 60 by PZ by 60A. See here, so EZ is proportional to flux produced per pole. At the same time, it is also proportional to the speed. Okay, so speed is in revolutions per minute. Okay, so to draw the characteristics of DC generators, to draw the characteristics of DC generators, we are assuming that generator is rotating with constant speed. So in that condition, or in that case, so generated EMF is proportional to flux per pole, right? Next, so coming to the open circuit characteristics, see here, so open circuit characteristics is a plot between is a plot between no load voltage and field current, right? Observe the graph here. So open circuit characteristics is the graph between, or plot between, the no load voltage or generated voltage to the field current, right? See, so the relation here, the graph is drawn for a fixed speed, right? See, whenever current in the field increases, flux produced per pole also increases, right? So here EZ is proportional to flux, right? Then generated EMF also increases, right? So see here it is not started at 0, it is started at some point A. Okay, so what is the reason behind this? The reason behind this is residual magnetism, right? What is mean by residual magnetism? In the sense, in ferromagnetic materials, when current is even though reduced to 0, there is still magnetic power left in the core. Okay, so this phenomena is called residual magnetism. Due to the residual magnetism, open circuit characteristics does not starts at zero. It starts at some with some value of voltage. That is nothing but the residual voltage. Usually we call it as residual voltage, right? See. See, next. See, ma. Then see, observe here. So IF is increasing, E naught is also increasing. See, but up to some point, this relationship it holds good. After that, core will get saturated. Up to D, it will increase. After that, core will get saturated. Even though you increase the field current, generated voltage will remain constant. So at that point we can say that core is saturated, right? So the OCC curve is just the magnetization curve, and it is practically similar for all types of generators, right? See, one thing you should keep in mind that the OCC curve is drawn for a DC generator at constant speed. See, observe here. This is the open circuit characteristics curve with different speeds. Okay, so N1, N2, and N3. So here N1 is less than N2, N2 is less than N3. So this is the open circuit characteristics of DC generator. Next one is internal or total characteristics. So internal or total characteristics is the relation between the unload generated EMF and the armature current IA. So it is the relation between EZ and IA. So EZ is always less than E naught. EZ is the unload generated voltage, and E naught is the no load voltage. Okay, so open circuit characteristics is drawn at no load condition, right? So it is the plot between E naught and IF, whereas internal characteristics is the graph between unload generated voltage and armature current IA. Okay, so here EZ can be determined by subtracting the drop due to demagnetizing effect of armature reaction from no load voltage E naught. Okay, so EZ equal to E naught minus drop due to the demagnetizing effect of armature reaction. Okay, so therefore internal characteristics curve lies below open circuit characteristics curve. See, observe here. Here AB is no load voltage versus load current IL, whereas AC is unload generated EMF EZ versus load current IL. That is nothing but internal characteristics. And whereas coming to the external characteristics, so here see, observe the plot here. AD is the external characteristics. So which is the graph between terminal voltage and load current. Okay, so the terminal voltage V is less than generated EMF EZ due to voltage drop in the armature circuit. So here V equal to EZ minus IARA, right? So therefore the external characteristics curve lies below the internal characteristics curve. So external characteristics are very important to determine the suitability of a generator for a given purpose. Okay, ma. So external characteristics curve is very important to determine the suitability of a generator for a given purpose. Okay, see here. So AD is the external characteristics, right? See, ma. So whenever when load resistance is decreased in DC shunt generator, load current, what happens to the load current? Load current starts increasing, but load resistance can be decreased up to a certain limit only. Beyond this limit, any further decrease in load resistance results in decreasing load current and terminal voltage. So consequently, the external characteristic curve turns back. See, so observe the dotted line of the curve. See, even though you decrease the load resistance beyond certain limit, it will affect the current. So this is the characteristics of DC series generator. So here the curve AB is identical to open circuit characteristics curve. So AB is nothing but open circuit characteristics curve. Why? Because in DC generators, field winding is connected in series with the armature and load. So if it is connected in series with the armature and load, here IA equal to IL equal to ISC. So ISC in the sense field current in the series field winding. Okay. So field current is similar to load current. So the curve OC and OD represents the internal and external characteristics. So OC is the internal characteristics. So here also OC internal characteristics is a plot between on-load generated voltage and load armature current IA. So here EZ is E0 minus drop due to the demagnetization effect of armature reaction, and whereas OD represents the external characteristics curve. So external characteristics curve is plot between terminal voltage and load current IL. So here V versus IL. So V is equal to EZ minus IARA drop. Okay. So here also, even though you increase the load resistance beyond certain limit, the load current starts decreasing and the curve turns back. Okay, ma, hope you are understanding. So this is about the characteristics of DC series generator. Last one is characteristics of DC compound generator. Characteristics of DC compound generator. See, so in case of compound generator, there will be two field windings. One is series field winding, another one is the shunt field winding. Okay, so here we are having three types of compound generators. One is under compound generator, then flat compound and over compound generators. So this classification is done depending upon the direction of field currents. Okay, so if series winding is adjusted so that increase in load current causes increase in terminal voltage, then such generator is called over compound generator. Okay, so the adjustment in the field current increases the load current. So in that case, that generator is called as over compound generator. If series winding is adjusted in such a way that voltage remains constant even though load current is increased, then that generator is flat compounded. Okay, so it won't affect the voltage. And coming to the under compound generator, here series winding has lesser number of turns compared to the shunt winding. Okay, so here ISC opposes the ISH. Okay, mom. So that generator is nothing but a under compound generator. See, so one more compound generator is cumulative compound generator. So here terminal voltage drop from no load to full load in a shunt generator can be overcompensated by use of an aiding series field. See, so here we are going to aid the ampere turns in series field, which automatically increase with the load, so that thus compensates the armature voltage drop. And one more classification of compound generator is differential compound generator. So differential compounding is not used in practice as the terminal voltage falls off steeply with load. Okay, so it is not used in practically. Okay, hope you understood the class. So in this class we have discussed about the characteristics of generators. We have three types of characteristics of generators. One is open circuit characteristics, second one is internal characteristics or total characteristics, third one is external characteristics. Right? Thank you.